Hello, this is Mr. Henry, and welcome to Lesson 2.2, Geometric Transformations. The essential question says, how do I apply properties of rotations, reflections, and translations? The warm-up question asks, how do you determine if a transformation is a rotation, reflection, or a translation? So hopefully you remember from when you did the Explore activity before Lesson 2.1 or during Lesson 2.1 that a translation is when you have a shape and it just moves from one place to another. So it's sometimes referred to as a slide or a glide or a move. So that's a translation. A rotation is like a spin. So if I have I don't know, a smiley face, a rotation, if I rotate it this way, my smiley face would then be sideways. And a reflection is like a mirror image. Trying to think of something, how about like a sideways house thing. And if I reflect it across this line, now the sideways house thing looks like that. So that would be a mirror image, and that's a reflection. And so really that's what this part of this module is about, is just being able to recognize, yes, that is a rotation, that is a reflection, that's a translation. Being able to know what they are, being able to see them. And in the next module, we'll get in more detail, more depth with these transformations. But here we have a couple vocabulary words. The first of them here is the corresponding parts. So corresponding parts, it says it's a part in the same position but from the other object. And what that means is if you have two objects, say they came from a transformation. So let's just say, for example, I did a slide, a rotation, a translation. So if I have, I'll make the little house thing again. There's one, and then I slide it this way, so many units, and there's the same thing. So a corresponding part would be a part that's in the same position but on the other object. So this bottom left-hand corner, those corners are corresponding parts. The part I'm highlighting in green here, that side corresponds to that side. Those would be corresponding parts. They're the same parts but in the other object. That's what corresponding parts mean. A rigid transformation, something that was talked about during that exploratory lesson at the beginning, but a rigid transformation is a transformation where the shape of the object remains the same, even if it's in a new location. So the word rigid means it doesn't change shape. So a rigid transformation is a transformation where the pre-image and the image are congruent. They're the same shape. They have the same angle measures, the same side measures. It's the same shape, even though they may not be in the exact same position. One might be turned or flipped, but it's still the same shape. And this word, rigid transformation, is also called an isometry. But for the most part, you'll just need to know it's called a rigid transformation. Now, you heard me use the word congruent a second ago, talking about rigid transformations have congruent angles and congruent sides. Well, the word congruent means it's two objects that are exactly the same. Same size, same shape, but they don't necessarily have to be in the exact same position. So two angles, if they're both 30 degrees, would be congruent. That 30-degree angle is congruent to that 30-degree angle. They're the same measure, same shape, even though they're not in the same position. So in this first example, what we're trying to do is figure out, is this showing a rigid transformation? So let's see. This first one, so the black shape, since it's the A, B, that is the pre-image. So that's the original. That's what it started out as. And then it changed into this gray one. That's the A prime, B prime. So let's see. This does not show a rigid transformation because this is not the exact same as this. If I look at corresponding parts, for example, this part here is not the same size as that part there. So those are not rigid transformations. There. So not a rigid transformation. The parts are different sizes. Letter B. Looking at it, I don't see anything that looks terribly far off. I mean, this side looks to be the same as this side. Those are corresponding. They look to be about the same size. And same thing with like this side here and this side here. They appear to be the same size. So I would say those look like rigid transformations. And also, I mean, besides looking at just the length of the sides, you can also look at the angles. This looks like a right angle. That looks like a right angle. The measurement here looks similar to the measurement there. So the sides should all be the same length, and the angles should all be the same. And they appear to be the same in this example. Now, in this example here, letter C, I want you to tell me, does this show a rigid transformation? Why or why not? Pause the video, do it on your own. When you're ready to continue, hit play, and we'll go through it together. Alright, so let's see here. We have, this would be, I guess, our primary shape. So maybe call that A, and then this would be like A prime here. So is that a rigid transformation? Well, right now I'm looking at the lengths of the sides. So this side here and that side here. I mean, those sides all appear to be the same. So I don't see anything off there. The height of the object, which is this side, and the height of the object, everything appears to be the same in this. I mean, it looks like a rectangular prism, so all the angles would be 90-degree angles. So as far as I can tell, this is a rigid transformation. So it's a rigid transformation as far as I can tell because all the angles appear to be the same and all the sides appear to be the same. They're congruent. They're the same length, the same measure. So, in your own words, what makes a rigid transformation? Well, in my mind, it's those two things we just said. It has to do with the angle measures have to be congruent and the side lengths have to be congruent. In essence, the two shapes need to be like identical mirror images of each other. They just may not be in the same place or facing the same way or rotated the same way, but they're still congruent. Or if I make some funky shape here, and then I clone it, no matter what I do to this shape, if I rotate it, those two are still rigid transformations. It came from the same thing. If I place the one over top of the other, they're identical. So I can rotate it, I can flip it, flip, left, right, there it is. Still, it's the exact same shape. I can slide it, I can rotate some more. Those are rigid transformations because my original shape did not change. The angles are the same, the side lengths are the same, they're clones of each other. So, example 2. Now we're going to be looking at some of the properties of these rigid transformations. Because we know that the angle measures are the same and the side lengths are the same, they're congruent, we can actually do a little bit of math with some of these geometric shapes because of that. So here it says, the pre-image of triangle ABC has an area of 9 feet. All right, that sounds important. So this guy has an area of 9 feet squared. All right. The image is then flipped across the x-axis and rotated 45 degrees. And there's the image there, okay? What is the area of A prime, B prime, C prime. So we're trying to find the area of that triangle. Well, if you start thinking too hard about this problem, you're probably starting to think, okay, the area of a triangle is 1/2 the base times the height, but we don't know the base and we don't know the height. That's if you're thinking too hard. If you step back a second and go, wait, these two shapes are identical, which means if the first shape has an area of 9, then the other shape has to have the same area because it would have the same base, the same height, so both parts would go into the same formula. You get the same answer. So what is the area of image A prime, B prime, C prime? It's 9 feet squared. And that's all there is to it. Recognizing that the shapes are congruent, they are the same, they have the same area. Letter B. Letter B says find all of the missing sides and angles in both figures. Okay, so first thing I'm doing is I'm looking and I see I've got A, B, C, D, A prime, B prime, C prime, D prime. Okay, so if you match it up, this A, B would match up with A prime, B prime. So AB here is 12, so this A prime, B prime would be 12 inches. Let me see. I think I have a way to maybe make these sides a little bit easier to understand. So let me highlight here. So this AB is here, and AB is here. And then we've got BC, B prime, C prime, CD, C prime, D prime, and AD, A prime, D prime. Alright, so now we can tell that this was kind of like a reflection because my shape is now backwards, flipped left-right of how it was originally. Alright, so still, this yellow side, the AB, A prime, B prime, is still 12 inches. I'm agreed. Okay, so what other things are missing? Well, I don't have a length for this DC. So if I look at the image, C prime, D prime is 8, so this side must still be 8 inches because the sides are congruent. They're the same length. Alright, looking at side length, so I don't have AD, which it says is 6, so A prime, D prime is 6, so AD is 6. Alright, so my pre-image, the bottom shape, I have all of the sides filled in. Now let's fill in all the sides in the top. So I've got A prime, B prime, I need B prime, C prime. So if I look at BC, 7 inches. And I have all my sides filled in. Okay, so now I'm missing angles. So I need to find this angle, this angle, this angle, and that angle. So I guess one at a time. So I'm looking for A, B, C. A prime, B prime, C prime is 60 degrees. Corresponding parts are congruent. They're the same length, same size. So looking for BCD. BCD is 95, so 95. And lastly, we've got our other 2 points here, so let's do this quickly. BAD is 80, so 80 degrees. And finally, this angle D prime is 125, so that's 125. So our picture got a little cramped here towards the end, but still, we were able to find missing pieces of these congruent shapes because the corresponding parts are congruent. They're the same size. Pretty easy. And last thing we've got is we've got some applications. So let's see here. Or this letter C. It says, in the trapezoid ABCD from problem B, okay, the one we just did, ABCD from problem B, okay, so we're talking about that trapezoid there. Sides AB and DC were parallel. AB and DC were parallel. Yes, I'll agree. That side and that side appear to be parallel, okay? Were they still parallel after the transformation? So let's see. So after the transformation, I'm looking for A prime, B prime, and C prime, D prime. Do they still appear to be parallel? Yeah, they do. Those lines still appear to be parallel to each other. So were they still parallel after the transformation? Yes, they were still parallel. Would they still be parallel after another transformation where A prime, B prime, C prime, D prime were reflected across the x-axis, and how do you know? So if I took this image and I reflected across the x-axis, so it would be down here now, would they still be parallel? And the answer would be yeah, of course they'd still be parallel, because again, these transformations are rigid, so the shape did not change. Even though I'm reflecting across the x-axis, it'll still be the same. So yeah, yes, it would still be parallel. And how do you know? Well, because they're rigid transformations. They are rigid transformations. Alright, so example 3a says James traces the shape of a picture of a dragon on tracing paper. If James moved this paper in any direction, including turning, flipping it over, would this be a rigid transformation, and why? Well, I think so. So if I took a dragon here, so a little rar, leg, wing, that is a sweet dragon. Alright, so there's my awesome dragon. So there's my shape. So if I take this and it says, and move the paper in any direction, so imagine this is my paper and I move it this way. Yes, that's still a rigid transformation because the shape didn't change. Okay. If I turn it, if I rotate the paper, yeah, it's still staying the same. The angles aren't changing. The length of this wing's not changing, so that's still rigid. What about flipping it over? If I flip it over this, flip left and right, yep, length of the wing stayed the same. If I flip it up and down, what are you doing? If I flip it up and down, yep, the length of the wing stayed the same. So yes, that would still be a rigid transformation. No matter what you can do to that piece of paper, that's going to stay a rigid transformation. So yes, this would be a rigid transformation. Because each of those effects, turning it, flipping it over, rotating it, you're not changing the size of the original image. I'm going to say because the original image was not changed in any way. So the original image was not changed in any way. It wasn't made bigger, wasn't made smaller, wasn't distorted. Okay, so let's check out example 3b. What if James drew a picture of a dragon on a fully inflated balloon, then gave the balloon to his sister, who deflated it? Would the picture of the dragon still be a rigid transformation? Why or why not? Go ahead, pause the video, and try this one on your own. When you're ready to continue, hit play, and we'll go through it together. Alright, so if I have a big old balloon here, and there's a picture of a dragon on it. Grr, arg, leg, leg. Yeah, beautiful dragon. Alright, and I took this whole picture of a dragon, and I gave it to my sister, and then she deflated it. Is that still a rigid transformation? Well, no, of course not. From how it started here, look at the length of the size of that wing. And then you give it to your sister and she deflates it. Look at that. That wing is now much smaller. So the length of the sides did not stay the same. So this would not be a rigid transformation. So what you would write down, not a rigid transformation because the length of the sides did not stay the same. Alright, example C. It says triangle ABC has measures, alright, triangle, A, B, C. Alright, so measure of angle A is 85 degrees. Sweet. Measure of angle C is 20. Awesome. The triangle is reflected across the y-axis. Okay, so here's my y-axis, and it flips like this. So I'd have C prime, A prime, B prime. What are the measures of angles A prime, B prime, and C prime? Okay, well, the fact that I drew a picture here as I was reading it, I've actually done most of the work already. I really encourage you to draw pictures when you get to word problems because they help you understand what's going on. So there's my ABC. I put in the measurements that it told me in the problem. This is the y-axis that I was reflecting across. So now I got to figure out what are the measures. Well, we learned in this lesson that corresponding angles are congruent. So C is 20, C prime is 20. A was 85 degrees, A prime 85 degrees. The only one I don't know, or I can't tell by looking at the picture right away, is this angle B. Well, maybe you remember back in some other geometry class or some earlier grade that the angles of a triangle, if you would add all the angles together, if you'd add A prime plus B prime plus C prime, it has to equal 180 degrees. That's every triangle. So if A prime is 85, B prime I don't know, so I'm going to put an X. C prime is 20. What number would we plug in here to make this side equal 180 degrees? Well, you can do some guess and check, or you can actually solve the equation. Minus 20 minus 20. So 85 plus x equals 160. Minus 85 minus 85. X equals, handy dandy calculator, just don't want to make a mistake. 160 minus 85 equals 75 degrees. So that x, this missing angle, would be 75. That's not 75. 75 degrees. So we had to use the fact that we knew that all the angles of a triangle add up to 180, just kind of like how a rectangle or a quadrilateral, any four-sided thing, all the angles add up to 360. Maybe you didn't know that. Letter D. Perfectly identical twin brothers Sam and Jake took a vacation to different locations. Sam went to Hollywood, California, and Jake went to SeaWorld in Florida. Sam is 5 feet 8 inches tall. How tall would Jake be? Go ahead, pause the video, answer the question, and hit play when you're ready to continue. Alright, so this was kind of like my best attempt to try to come up with an example of a translation in real life. So I have two identical twin brothers, Sam and Jake. And they're both 5 feet 8 inches tall. So there's 5 foot 8 inch tall Sam and clone. There's his identical twin brother, 5 foot 8 inch tall Jake. Sam went to California. Jake went to Florida. How tall is Jake? Well, if the two brothers are identical, then they'd still be the same height. Jake is 5 feet 8 inches tall. That's our answer. Last one. It says Nicole uses a magnifying glass to read some small writing. If you use the original text as the pre-image and the view of the text through the magnifying glass as the image, would this be a rigid transformation? And then why? Pause the video, do it on your own. When you're ready, continue, hit play, and we'll go through it together. Alright, so hopefully maybe you drew a picture. So I'm imagining, you have your little text in a piece of paper or a book or something, and then you take out your magnifying glass, and now the letters are much bigger. So would this be a rigid transformation? No, because the size of the letters changed. They were like really tiny T, and then you look at it through a magnifying glass, and now it's a really big T. The lengths of each side changed. So that is not a rigid transformation. Would this be a rigid transformation? No. It's not a rigid transformation because because the lengths of the sides changed from the original image to the new image. And finally, what are the properties of a rigid transformation? These transformations we learned about in this lesson, what properties existed in every single one of them? Go ahead and answer that question. Okie dokie, here's what I came up with. I said in each example the corresponding sides were congruent and the corresponding angles were also congruent. The images were clones of each other. So that's what makes something rigid. The two shapes are identical. This has been lesson 2.2. Thank you for watching.